So section 9.3 is about figuring out the error when you approximate a function using a Taylor polynomial. All right. Just a reminder that you're responsible for kind of knowing quickly what the Maclaurin series is. So I'm giving you a second to look at this one and see if you can remember which function that is. If you said it was the sine function, nice, you're remembering that sine is an odd function, so this is the odd one. And this is, it so happens, this converges for all x's, as long as you have infinitely many terms. If you don't have infinitely many terms, then it's not exactly the sine function. It's closer to the sine function when you're closer to 0, but if you get further out, if you have, the fewer terms you have, the less like the sine function it is. So in the real world, we can't really add infinitely many terms, so we want to figure out how many terms is good enough. It turns out that your calculator, when it graphs the sine function, isn't really graphing the sine function. It's graphing a Taylor polynomial approximation of the sine function. It's just that it uses so many terms that it's good enough, and it looks like the sine function for all intents and purposes. So an example of this type of problem is we're trying to figure out a Taylor polynomial for the sine function, but we want it to be accurate on the interval from negative pi to pi to 0.0001. We want it to be accurate within that degree. So in other words, what I'm saying is we have the function sine of x, and we have some Taylor polynomial, which looks like x minus x squared, x to the third over 3 factorial, plus x to the fourth over 4 factorial, no, fifth, sorry, it's the odd one, x to the fifth over 5 factorial, etc. And we don't know how many terms we need, but we want to make sure that the error, that if I did p of x minus f of x, and I'm going to just put it in absolute value because I only care about the magnitude of the error. I don't care about the sign of the error. If I subtract those two functions, I want to make sure that that is less than or equal to 0.0001 on negative pi is less than x is less than pi. Okay, so I want to make sure that I have enough terms that this is true. This is definitely a machine question. It's a graphing calculator question. So go ahead and grab your graphing calculator. And I'm going to open up a new window. And we're going to add a graph. So I can graph sine of x, and that's whatever Taylor polynomial our calculator uses to approximate sine of x, but it's a really good one. It has a ton of terms. If I hit tab, I can graph something else, and I could graph just one term of the Taylor polynomial. So if I use a polynomial of degree 1, as long as I'm really close to 0, these two graphs are pretty much the same thing, but as I get farther from 0, it's less good. It's less of a good approximation. I'm going to make another function that just shows me the error. So the error is going to be the difference between the two, of the difference of f1 of x minus f2 of x. So it's just sine of x function minus the polynomial. Right now the polynomial is really just a degree 1 polynomial. So if I'm at 0, my error is 0, but as I get farther away from 0 in both directions, my error gets bigger. Okay, so I'm going to change my window. I would like my error to be from negative pi to pi. So that's what I want my domain to be. And I can see that f of x equals x is not a very good approximation for sine of x. if I'm out even this far, it's not very good. I'm going to go ahead and make a graph of that, the size of the air. I want the air to be this big. It's hard to see that line, so I'm going to change my window again. I'm just going to change my window to be from between 0 and 0.002, so I can see that line right in the middle. Now, the scale changed, and I can't really see the sine function anymore, but I don't care about that. I really care about the air. So this black line shows me the air. It shows me the difference between the sine function and the Taylor polynomial. And I want my air to be smaller than this horizontal line, and I want it to be smaller than this horizontal line all the way from negative pi to pi. Right now it is smaller than the horizontal line, but not from negative pi to pi. It's only smaller from here to here. So my approximation with using just one term is not good enough. So what I'm going to do is I'm going to edit my function. I'm going to edit my f2 function. So it's not just x. It's going to be, I'm going to do a third degree polynomial. And now it's a little better. See how my air is now, it's below that interval, below that line on a larger interval. But it's still not good enough because I want it to be good between negative pi, and it's only good between here and here. So I can add more terms to make it even better. And I feel like it's probably going to take more than just one more term, so I'm going to go ahead and make it into a 7th degree polynomial and take a look at it. So it's getting better. My air is below that line on a larger interval now, but it's not below that line from negative pi to pi, so I don't have enough terms. I need to add some more. So this is really just like calculus guess and check at this point. I'm just plugging in more terms so that I can see where my air is small enough. Okay. Now for any x coordinate between here and here, my air is below 0.0001, but that's not good enough, so I would have to add more terms. Okay, now it looks like my air, which is way down here, is small enough. It's below that pink line on that whole interval. I don't know for sure if I put too many terms in there. So if I wanted to check to make sure that I didn't put too many terms in, I could take this 13th term off. And it looks like 11 is not good enough. So I would need, the polynomial I would need to use to approximate sine of x on this interval in order for my air to be small enough would be a 13th degree sine of x polynomial. So this would be the polynomial with that x to the 13th term back on. Okay, so the answer to the question is this function all the way out to x to the 13th over 13 factorial. If I use this polynomial for any x between negative pi and pi, my air is going to be smaller than 0.001. So visually, you might have seen that or not, but visually the sine of x function looks like this. If I use a first degree polynomial, it's that straight line, which is dead on at 0, but gets further off the further out we go. If I use a third degree polynomial, it's now this cubic function, which is even better than the straight line, but not as good as if I use a 5th degree polynomial. And the more terms I get, the better my approximation is to what the actual sine function looks like. And we made a graph of the air. I'm going to leave this as an exercise for you to try. You can figure out a Taylor polynomial for e to the x that's accurate to 0.001 using that same technique. I will tell you that it turns out you need a 9th degree polynomial in order to be accurate enough. You can ask questions in class if you're not sure how to figure that out. The other thing you need to learn today is how to deal with an error formula for a geometric series. So we're going to kind of think the same way. This is a geometric series because we're starting with a equals 1, and each time we're multiplying by x squared. So that means that our function is a over 1 minus r. And we are going to use this, we're going to truncate it, so we're not going to use the whole thing. If we were going to use the whole thing, that would be 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th, and then it would be x to the 2n, and it would be infinitely many terms. But of course in the real world we can't really use infinitely many terms. So instead we've decided we're going to truncate our polynomial. So we're only going to use out until x to the 6th. We're going to use a 6th degree polynomial to approximate it. Okay, so if I look at the difference, if I look at f of x minus p of x, this is going to be the error. So if I subtract these two functions, the 1's are going to subtract away. The x squareds would subtract away, the x to the 4th would subtract away, and the x to the 6th would subtract away, and I'd be left with x to the 8th plus x to the 10th, etc. And this is my error. This is how much I missed by truncating the polynomial. The other thing about this infinite polynomial now that's left is that it is also geometric. And it's geometric starting at x to the 8th and still with a multiplier of x squared. So I could write that geometric polynomial as x to the 8th over 1 minus x squared. The only time I can write a formula for the truncation error is if I have a geometric series. And this is the exact error if I truncate instead of using all infinitely many terms in my polynomial. And the error varies depending on what my x coordinate is. So if I wanted to evaluate this function, this error function, at like 0.5, that would tell me what is the difference between the actual function, this thing, evaluated at 0.5, and using a 6th degree polynomial to approximate the function at 0.5. What's the difference between those two values? How good is it to use that approximation? So that's what that function tells us. I'll leave you another one to try. This gives you your error would be geometric, so you should be able to write the truncation error formula. For this weekend's homework, there is not a Khan Academy lesson, so your job is to do the book homework problems in order to get the practice you need. Thank you so much.